My name is Sandy Schaefer, and I am an instructor with the Educational Services team in Washington, D.C. Joining me today is Dr. Lauren Scott from the Geoprocessing team in Redlands. We would like to welcome you to the live training seminar on understanding spatial statistics in ArcGIS 9. In today's seminar, we will discuss three main topics. First, we will talk about some basic concepts of spatial statistics. Then we will show you ways that you can explore your spatial data using spatial statistics. We will discuss ways of measuring the distribution of your spatial features, as well as ways to determine if your data has any spatial patterns. Throughout the presentation, we will be discussing examples on how to use the ArcGIS spatial statistics tools. We will conduct some software demonstrations, and we will have review periods followed by a question and answer session, during which time Lauren will answer some of your questions. So let's get started with our first topic, the basics of spatial statistics and the tools available to you in the core ArcGIS 9 product. So what are spatial statistics? They are exploratory tools that help you measure spatial processes, spatial distributions, and spatial relationships. There are a lot of different types of spatial statistics, but they are all designed to examine spatial patterns and processes. Please understand that when we talk about spatial statistics, we are not talking about applying traditional aspatial or non-spatial statistics, like what you may have learned in your high school stats class, to spatial data. When we talk about spatial statistics, we are describing specific methods that use distance, space, and spatial relationships as part of the math for their computations. Oh, we're still going to talk about mean and standard deviation, but our focus will be on how those concepts apply to spatial features. Today we will focus on a particular type of spatial statistics, often referred to as pattern analysis. The tools I'll be describing fall into two broad categories. The first category is descriptive in nature. These tools quantify or identify characteristics of features. They answer questions like, where is the center? Or, how are features distributed around the center? The second category is more concerned with describing spatial pattern. With these stats, we are able to determine if our features are random, clustered, or evenly dispersed across the study area. So why do we use spatial stats? Spatial statistics is one of many approaches that can help us assess or analyze our data, and it's pretty powerful too. Why? Well, because with spatial stats we get a better understanding of geographic phenomena. Think about it. Everything happens in space and time. When we analyze data outside of their spatial context, we really only get half of the story. As geographers and GIS analysts, we're especially interested in the spatial aspects and impacts of our data. Spatial stats can also help us pinpoint causes of specific geographic patterns. One of the easiest analyses we can do is to map different phenomena, then overlay the maps to see if we notice correlations. For example, we might find that a certain disease is only found in villages near rivers and streams. Perhaps our disease is being spread by a river parasite. Spatial stats can also help us make decisions with a higher level of confidence. So you've done your analysis and you've come up with some conclusions or recommendations. Your boss is going to want to know how you came up with those conclusions, right? You can say that visual inspection indicates, or my research suggests, but it's great if you can also add, and my results are statistically significant at the 0.05 level. It gives you a lot more confidence in your decisions and your conclusions. Finally, spatial stats are helpful when we are dealing with large, complex data sets, which is exactly what we deal with in GIS every day. Spatial stats often allow us to cut through some of the noise and complexity in our data to get straight at the broader trends or overall patterns. We are able to summarize our data and talk about averages, rates, or trends. ArcGIS 9 comes packaged with the spatial statistics tools needed for doing spatial distribution and pattern analysis. The tools are located in the Spatial Statistics Tools toolbox shown here. In this seminar, we will concentrate our time on 3 of the 4 tool sets. It is important to understand that these tools are core functionality included in ArcGIS 9. They are not a separate extension that you have to purchase. Also, these tools are available at all license levels: ArcView, ArcEditor, and ArcInfo. What is really nice about these tools is the source code is provided. The tools are packaged in the form of scripts and models. You can look at the script and see the algorithms and mathematics for these tools, so they are great in a teaching environment. And if needed, you can edit copies of the provided scripts to create new tools or different implementations of these tools. So let's go to our first software demonstration. All of our demos today will use crime data from a city in the United States, but I would like to take a moment to remind you that these tools can be used on a large variety of data and for lots of different applications, such as epidemiology, archaeology, and wildlife biology, just to name a few. In this first demo, I want to emphasize why you might want to supplement traditional GIS analysis with spatial statistics. Police resources are limited. They can't be everywhere all the time. So it's important to use the resources we have as effectively as possible. If we can identify where the crime hotspots are located, we can make better decisions about where we might want to increase law enforcement presence. Before we had GIS technology, police departments would typically use pushpin maps to show spatial patterns in crimes. Let me turn on a digital replica of a pushpin map. So let's pretend that this is a wall map and we've stuck pushpins in it to represent crime. In 2002, there were over 40,000 crimes reported in this city. Can we effectively determine our crime hotspots from this map? It looks like we need to have patrol cars almost everywhere. And we really can't see more than a general citywide pattern. So you can see that visually assessing the data with pushpins isn't very easy. Now, there was a natural progression in crime mapping as more police departments were using GIS, and that was to create density maps of crimes. Now, to create a density map, I used the point density tool available with the Spatial Analyst extension. The result is a classified map that shows relatively where crime is high, those are the red spots, and where crime is low, that's the bluer area. The tricky part about creating density maps is we have to make decisions about a couple of parameters. One of those is the neighborhood size, the distance value which tells the software how much area around each feature it should consider in the calculations. Selecting this distance can be subjective, and the value you select can have a big impact on the results you get. The density we are looking at here was created using 1/8 of a mile. I also created a density map using a 1-mile neighborhood. I used the same data, I just changed the distance value. With that distance, I get a different picture, bigger concentrations, and a lot more gradation. But this isn't the only choice we have to make with density maps. Once you have your values, you need to make a decision about how to render or symbolize the density values. Which range of values will indicate high crimes, our red, and which range of values will indicate low crimes, our blue. ArcGIS offers several options that you can choose from. In the next few maps I'm going to show you, the underlying density values remain fixed. I used the results from the 1-mile density map we're looking at here. The only thing changed is the rendering scheme. This map is rendered with the Jenks natural breaks. For this layer, I used equal area rendering. I can see that I get higher crime areas that are more compressed or compacted. Another option is quantile. With this, I get a much different picture. Crime is much more widespread. Again, we want to identify crime hotspots so we can make better decisions about how to allocate police resources. But we still haven't been completely successful with this. Now, it's not that we can't see a pattern with the density maps. It's that we get different patterns depending on the distance value and rendering scheme that we use. Here's where Spatial Stats can step in and help out a great deal. This final map that I'm going to show you was created using the Hotspot Analysis tool. Later, I will outline exactly how to do the hotspot analysis. Right now, I want you to notice two things. First of all, unlike with the pushpin map where we had trouble identifying distinct patterns, here it is easy to see where our hotspots are. They are shown in red. We can also see where we have cold spots, those places where we have very few crimes. The second thing I want to point out is that there is less subjectivity when we use spatial statistics than there is when we use density mapping. The Spatial Statistics toolbox includes tools to identify an appropriate scale for my analysis. And the rendering is straightforward. A census block is either statistically significant or it's not. So with a statistical approach to analyzing crime, we accomplished our goal. We get a clear picture of crime hot and cold spots, which help us make better decisions about where and how to allocate police resources. In this section, we introduce spatial stats as a method of exploring your data to see what's going on spatially. We also talked about why you might want to use spatial stats to quantify patterns and relationships in your data. Finally, we talked about how the Spatial Stats Toolbox in ArcGIS 9 is not an extension, but rather part of the core product available at all license levels. I will now turn the seminar over to Lauren, who will answer some of your questions.
Thanks, Sandy. Our first question comes from the Woodland GIS class in Saskatchewan, and they're asking, can you use the spatial statistic tools in Model Builder? The answer is yes. The spatial statistics tools work like all of the geoprocessing tools. You can use them in Model Builder. You can call them from the command line. You can run them as a tool dialog, and you can also use them in scripts like Python scripts or VBA scripts. Several people have asked questions while asking about specific tools in Geostatistical Analyst and Spatial Analyst, and so I want to tell you just a little bit about how the tools that we're talking about today relate to the statistical tools in Geostatistical Analyst and Spatial Analyst. The tools that we're showing you today are core functionality, and what that means is that if you have ArcGIS 9, you have these tools, and you also have the source code for these tools. The Geostatistical Analyst and Spatial Analyst products, those are extensions. It means if you want those tools, you would purchase them in addition to ArcGIS. The tools we're showing you today are really very different than the tools in the Geostatistical Analyst or Spatial Analyst. And actually there's several products that have other types of spatial statistics as well, including Business Analyst, and also we have something called the SAS Bridge. But the statistics in those products are used for different applications, and usually they're typically used to answer different types of questions. The Geostatistical Analyst tool product contains powerful tools that create surfaces or to predict values for a surface. So you would use Geostatistical Analyst if you were working with sample data. If you're in the mining or the petroleum industries, for example, you're probably already using Geostatistical Analyst. The Spatial Analyst product includes very powerful tools for working with raster data. Now, raster data analysis has been around for a long time, so there's really a very rich collection of tools in the Spatial Analyst product, including some multivariate statistical tools and also some very powerful tools to do hydrology type analysis. The tools in the Spatial Statistics toolbox that we're showing you today, I think we could say that they would fall into a category that we might call pattern analysis methods. In the academic literature, these methods are usually referred to as point pattern analysis, but all of the tools, with just one or two exceptions, work with just fine with points, with lines, or polygon features, so it's really more appropriate to call them pattern analysis tools. Let's see. And I think with that, I'm going to turn back to Sandy.
Thank you, Lauren. Now let's talk about how we can measure the spatial distributions of our features. When we measure the distributions of spatial features, we're interested in answering simple questions. Where is the geographic center of all my features? Or which feature is most centrally located? Or how are features dispersed around the center? The tools in the Measuring Geographic Distributions toolset are the tools you will need to answer these and other simple questions about your data. Often, these tools are used to compare the distributions of different features. For example, in this graphic, we're looking at cases of dengue fever for a village in India. We wanted to know how the distribution of the disease changed during the first 3 weeks after the outbreak. The standard deviational ellipse tool we used, which we'll talk about more in a few slides, shows us that the disease started in the southwest corner of the village, spread along the primary transportation corridors, and by week 3 encompassed most all of the village. So let's take a closer look at the tools in this toolbox. Now, when examining your feature distributions, one question you might ask is, where's the center of my distribution? To answer this question, you could use the mean center tool. This tool will compute the average x and y coordinate for all the features in your study area and generate a new point feature indicating the center. In the graphic, we have the counties in California. The mean center of all California counties is located where you see the red plus sign, just to the southwest of the elbow in California. More commonly, we would use the mean center tool to compare distributions of different types of features, or to find the center of features based off an attribute value. For example, using population data over the past 100 years as a weight for the mean center tool tells an interesting story. In the early 1900s, the mean center of the population was up in the midsection of the state, probably as a result of the gold rush. But over time, the population center has shifted down towards the southern portion of the state, most likely in response to manufacturing boom in aerospace engineering. Another question you may ask about your data is what feature is most centrally located. In contrast to the mean center, here we want to find the existing feature that is the most central to all other features. The tool we would use is called the central feature tool, and it identifies the feature that has the lowest total distance to all other features. For example, let's say we're in charge of finding the best location for a new health center for these 5 cities. In the graphic we see here, we don't really need a GIS to tell us which city is the most central. However, the central feature tool confirms what we see, that the most central city is Springfield. A more interesting example involves adding population and using that value as a weight in the analysis. When we use population as a weight, we change our question a bit. We're no longer asking which city is most central, but which city is most accessible to the greatest number of people. Because Baker has such a large population, placing the new health center there will maximize accessibility for the population as a whole. While the mean center and the central feature tools tell us about our center of our distribution, they don't tell us about the overall distribution. The standard distance tool tells us how dispersed our features are around that center. In the map shown, we have incidences for respiratory disease among children. We want to see if we can detect any seasonality for this disease. For example, do we see a peak of incidences when certain plants or pollens are present? To answer this question, we would examine the spatial distributions of the disease for each season. Output for the standard distance tool is a circle. When the circle is very large, we know that the cases are widespread, like our blue winter here. When the circle is very small, we know that the cases are more localized, like we see with spring. Comparing the standard distance circles for both seasons suggests this disease is exacerbated by cold winter temperatures. In addition to learning about the distribution of features, you might also need to identify distributional trends. The directional distribution standard ellipse tool is similar in idea to the standard distance tool, but it allows you to create what are called standard ellipses, indicating the orientation and direction of your distribution. In our graphic, a wildlife biologist studying bobcat movement between preferred habitat areas calculated the orientation of the movement areas. He wanted to see if the distribution coincided with natural features, such as valleys, rivers, or ridgelines. This could help provide clues to the travel routes the bobcats used. Let's go to our second demonstration. In this demo, we're going to revisit our city from the first demo. Now in this demo, I want to illustrate some of the ways that we might use descriptive statistics that we just talked about with crime data. We will be answering two questions. The first one looks at crimes involving domestic violence and asks, where should we locate a new support center to help victims of this particular type of crime? To get this data set, I did a spatial join which let me aggregate or count domestic violence incidences by census block for a particular community in our city. The community wants to create a new support center for victims of domestic violence. An obvious choice would be to put the new support facility right in the middle of the community. If we run the central feature tool, we can find the most central census block, located here in the center of our community. But what if the community wanted to place the support center so that it better serves the population at risk? The map shows the number of domestic violence incidences for each census block. To find the most accessible location to the population at risk, we would use the spatial distribution of past cases of domestic violence as a weight. Let's open the central feature tool. It's located in my Spatial Stats toolbox in the Measuring Geographic Distributions toolset. For this tool, for my input, I'm going to use the domestic violence layer. That's the census blocks that we were just looking at. My output, I'm actually going to place in a geodatabase that I've created just for these demos. I'm going to call it Central Feature Domestic Violence _ W, so that I know I've used a weight with it. For my weight field, this is where I'm going to put the past occurrences, and that column is the domestic violence column. And I'm going to click OK to run the tool. So it shouldn't take too long. Right now it's looking at our weights and seeing where the most central location is based on past occurrences of domestic violence. It looks like it's done. I'm just going to close Arc Toolbox, and I'm going to symbolize the results just a little bit differently so we can see them better. I'm going to left click on the symbol, and I'm going to change the outline color to a black, and I'm going to increase the outline width. So here we see our results, and from the results, it appears that more cases of domestic violence are located in the western part of the community. If our goal is to make the new facility most accessible to the population at risk, this would be the good area to put it. Okay, now let's use descriptive statistics to answer another question. We want to use crime attribute information to see if we can discern any temporal trends in occurrence. Our question is, does nighttime crime have a different spatial distribution than daytime crime? And we want to answer this question for each police beat in our city. If we observe a temporal difference in the crime patterns, then we will likely want to set up different patrol routes for the officers working the day shift, symbolized in blue, than for those working the night shift, symbolized in purple. We have constructed a unique code in this layer that identifies both the beat and the time that the crime occurred in. Was it in the day or was it in the night? We are going to use this code as our case field or our grouping field for our tool. This is going to tell the tool to do a separate analysis for the day crimes and the night crimes in every beat. So I'm going to open Arc Toolbox. And remember, back to the lecture, we talked about two spatial stats tools that help us look at the overall distributions of our features. They were the standard distance and directional distribution standard ellipse tools. The standard distance tool tells us how dispersed our features are around the mean center. The directional distribution standard ellipse tool tells us about the distribution of our features as well as if there's a directional trend or orientation in that distribution. Because we want to know about the orientation of our crimes, we'll use the directional distribution tool. Now for my input, I'm going to use the Crimes 2004, which is my point features of all my crime instances. My output ellipse, I'm going to save in that same geodatabase, and I'm just going to call it standard deviation ellipse. Now in this situation, I want to use a case field. That's my grouping value that specifies the time and the beat in which my crime occurred. And that column is this D or N underbar beat column. Even though this analysis only takes about 40 seconds to run, I wanted to set up some symbolization to best communicate my results. So I've already run this analysis. I'm going to cancel here and just show you the results. I'm going to close Arc Toolbox too. I'm going to turn on the standard ellipse by beat layer that I created. My daytime crimes are symbolized as a light blue, and my nighttime crimes are a dark purple. From the results, we can see that in most of the beats, there aren't any drastic differences between the occurrence times, distributions. Let's take a closer look. I'm going to zoom in to beat number 6. As you can see here in beat 6, the crimes for both the day shift and the night shift closely resemble a circle. The circular shape of the ellipse indicates that there isn't a strong orientation to the occurrence of the crimes. So for this particular beat, we can allocate police resources evenly throughout the beat during the day and night shifts. Now there is one beat where there appears to be a fairly strong difference between the day and the night, and that's in beat number 9. I'm going to zoom to that beat. In this beat, the first thing we see is a difference in the size of our ellipses. The night crimes are much more concentrated than those during the day. We can definitely set up patrol routes accordingly so that they are more concentrated during the night shift than the day shift. The second thing we see is the orientation of the crimes. Both ellipses have a southwest to northeast orientation. If we take a look at the major road network in this particular beat, we can see that there is a major road that runs from the southwest corner to the northeast corner of the beat. Could this road network be influencing the crime occurrence patterns? More analysis could help us determine if the roads are influencing crime locations. So in this section, we discussed ways of exploring the distributions of our features. We answered the questions, where's the mean center of my features, and which existing feature is the most central? The last two tools we talked about were standard distance and directional distribution. I'm now going to turn it back over to Lauren, who will again be answering some of your questions.
Thanks, Sandy. Yes, we got a question from Mike in Rocky Hill. His question is, can we calculate a weighted mean center? Sandy showed us how we could calculate a weighted central feature. And yes, you can. It works very similar to that. So for the mean center tool, you just specify the field that you want to use as your weight. And in fact, with ArcGIS 9.2, which is the next release, you'll be able to look at your features in 3 dimensions. So it would calculate the mean X, Y, and Z. We also got a call from Maria in Wagingen. Sorry, I kind of messed that up. Anyway, her question is, if your distribution is clustered into several clusters, could it be possible to get the center of each cluster instead of the center of the whole distribution? And the answer is yes. Many of the tools in the Measuring Geographic Distributions tool sets has a field called the case field. And what the case field does is it does allow you to group your features and to perform the analysis on each one of those groups. If you're asking if the tool automatically decides what the clusters are beforehand, the answer is no to that. That would be a really good tool. At this point, you have to identify the features that are associated with each group, and then run the tool. It'll compute the statistics separately for each group. We also got a call from Andrea in Boise. She wants to know, is it possible to use more than one field as a weight when I'm calculating the mean center or the standard distance? And the tools that allow you to specify a weight really do only allow you to select a single field for that weight. But do keep in mind that you could always create a new column in your table and compute some type of an index based on more than one field that summarizes the weights of several fields into a single index, and then use that index as your weight. We got a call from Blake in Missoula. He asks about the standard distance and standard ellipse tools that Sandy talked about. And They do notice that they ask the user to specify if they want 1, 2, or 3 standard deviations, and what exactly does that refer to. So that question tells me that you're using these tools, and that's great. Yes, both the standard distance and the standard ellipse tools ask the user to select the standard deviation level. And the simplest explanation is that you get a larger circle or a larger ellipse when you choose a value larger than 1, and 1 is the default. The more detailed explanation is, you have to think back to your high school statistics class here. You probably remember hearing about the normal distribution and the classic bell curve. Well, standard deviation is a measure of how the spread of your values are around the mean or around the average value in your data set. In a spatial context, the standard deviation is a measure of how your features are spread around the mean center location. So when our values are normally distributed, we know that 68% of all the values will fall within +1 and -1 standard deviations of the mean. We know that 95% of our values would fall between +2 and -2 standard deviations of the mean. So when we say we want to create a standard deviation ellipse with 1 standard deviation, we're asking for an ellipse that would encompass 68% of our features if, and this is an important if our features are normally distributed around the mean. And I'm going to turn it back over to Sandy.
Thank you, Lauren. Now let's talk about our next category of spatial statistics tools, spatial pattern analysis. These tools give us ways to measure the degree to which our features are clustered, dispersed, or randomly distributed across a study area. When we talk about analyzing spatial patterns, we are interested in finding out if there are underlying spatial processes influencing the location of our features. Are our features randomly located throughout the study area, or are they displaying a clustering or a dispersed pattern? We have 2 toolboxes in the ArcGIS for analyzing spatial patterns. These toolboxes contain different approaches to the analysis. The first approach, global calculations, identify the overall patterns or trends in the data. These types of statistics are very effective when we have a lot of complex, messy data, and we're interested in understanding broad overall trends. You can think of it as if you were taking all of your features and dumping them into the statistics crockpot. After they have simmered a bit, you will get a number or 2 that summarizes the overall spatial pattern of the data. Global type statistics are found in the Analyzing Patterns toolset. They work by comparing your feature locations and/or attributes to a theoretical random distribution in order to determine if you have statistically significant clustering or dispersion. The other type of statistic we have for analyzing patterns are categorized as local calculations. These calculations identify the extent and locations of clustering. They answer the question, where do we have spatial clustering? Local type calculations are found in the Mapping Clusters toolset. These statistics process every feature within the context of its neighboring features in order to determine whether or not it represents a spatial outlier or if it's part of a statistically significant spatial cluster. A global stats question that we might ask about our data is, are features clustered? The tool we could use to help us answer this question is called Spatial Autocorrelation Global Moran's Eye, found in the Analyzing Patterns toolset. Okay, so what is spatial autocorrelation, you ask? It's a complex sounding term with a simple explanation. The concept is based on Tobler's first law of geography, which says everything is related to everything else, but nearby things are more related than things that are far away. So with spatial autocorrelation, we are asking, are similar attribute values clustered in space? The output for this tool is a graphical display that gives you the results 4 different ways. It starts off at the top by giving you the statistical numbers. Under that, we have a pictorial representation of what those statistical numbers mean. The picture tells you if the pattern is dispersed or clustered. Under the graphic, we have a bar graph showing if the results are statistically significant. Finally, at the bottom of the dialog, the results are presented as a sentence. For the analysis presented here, the sentence says, there is less than a 1% likelihood that this clustered pattern could be the result of random chance. Let's look at an example. Before I explain it, please know that the analysis and results being presented here were done for demonstration purposes only. If we wanted to confirm or publish these results, we would have to do a more thorough investigation. In any case, we're showing here the number of new AIDS cases by county in California for both 1994 on the left and 2003 on the right. Our question is, how is AIDS spreading? Is it rapidly spreading outward from the high-risk areas to the surrounding counties, or is it remaining geographically fixed? Knowing this could help health authorities determine how to best address the problem. In the two thematic maps showing AIDS cases by county, we don't really get a clear understanding of how the disease is spreading. Overall, we know that the total number of new AIDS cases decreased each year between 1994 and 2003. And we see here that the distribution of new cases for each county is changing. But how? Let's look at the results of the spatial autocorrelation analysis. For 1994, we can see that new AIDS cases are clustered. Counties with lots of new cases are found next to counties that also have a high number of new cases. Now we ask, do they remain clustered in 2003? Is clustering of new AIDS cases becoming more intense or less intense over time? When we looked at new AIDS cases for 2003, we see that the z-score has increased. In 1994, the z-score was 2.7 standard deviations. In 2003, it is 3.7 standard deviations. This means that the clustering is more tense in 1994. When all the years were processed, the overall pattern was a slow increase in clustering, indicating that new cases are indeed remaining geographically fixed. In the previous slide, we asked a global question: is there clustering? Now we're going to switch gears and ask a local question: where are the clusters? Or, where do features with similar attribute values cluster spatially together? One of the tools in the Mapping Clusters toolset is called the Hotspot Analysis GETIS or GI star statistic, and it can be used to delineate clusters of features with values significantly higher or lower than the overall study area means or average value. This tool identifies clustering in both the high and low attribute values. A standardized z-score is calculated for each feature. A high z-score results when a feature has a high value and is surrounded by other features with high values. This is a hotspot. Similarly, a low z-score results when we have features with low values surrounded by other features with low values. This is a cold spot. An example we have for hotspot analysis uses mortality data for the eastern half of the United States. We wanted to know if there are persistent areas in the United States where people are either dying early or living longer than the average American. We used hotspot analysis to analyze 20 years worth of mortality data. The counties shown here in red are those where statistically significant early death hotspots for all 20 years. Similarly, the counties shown in blue are those that are statistically significant cold spots for early death for all 20 years. In other words, folks in the counties shaded in blue tend to live longer than the average American. Let's continue with our crime analysis. Now, in the first demo, I showed you a hotspot analysis map for our city based on all crimes, and I promised I would give you more details about how to do the hotspot analysis. So that's what we're going to do now. First, the context of the analysis. One of the communities in our city came to us and asked us to help them locate a suitable area for a vandalism prevention program. Their goal is to build a facility that will help reduce the spread of vandalism. One possibility would be to use the hotspot analysis tool to find those neighborhoods with lots of vandalism. We are looking at the vandalism per census block right now. But you can probably guess where the neighborhoods with a lot of vandalism are going to be. we expect to find lots of vandalism in the same neighborhoods where we have lots of crime, typically in our downtown and high-density neighborhoods. Let's see. I have a map here of our total crime per census block. And as we can see, we have a very similar picture. Our high vandalism is in fact in the same areas as high crime. An alternative to locate the prevention program in neighborhoods where vandalism is higher in proportion to total crime. To analyze this, we would divide the number of vandalism incidences by the number of all crime, creating a ratio of each census block. If we look at the ratio of vandalism to all crimes, we see a different pattern. It seems to be a bit more scattered and probably less concentrated in the city center. It's pretty interesting, but let's keep going and see what our statistics tell us. Now, performing a crime hotspot analysis involves 3 steps: aggregating the incident data, determining the most appropriate scale of the analysis, and then running the hotspot tool. The tools we will be using require weights, so our first step is to aggregate our crime data. I've already done that aggregation using a spatial join, and we looked at the counts of all crime and the counts of our vandalism already. The second thing we need to do before we run our hotspot analysis is to find an appropriate scale for our analysis. To do this, we use the Spatial Autocorrelation Global Moran's Eye tool. The Spatial Autocorrelation tool is in the Analyzing Patterns toolset, so I'm going to open our toolbox and I'm going to go to that toolset. This tool is going to help me determine the distance where the spatial processes promoting spatial clustering are most pronounced. Now, our input feature class for this tool is going to be our census blocks, and I'm going to use the count all crime per block. The input field is the attribute value that contains my weight or my count. We're interested in finding out where we have clustering of vandalism that is higher in relation to all crimes. So to find the most appropriate distance for evaluating clustering, I'm going to use the count of all of my crimes, total crime 02. This way, the distance that I find can act as a baseline if I want to run the same analysis for crimes other than vandalism. I'm going to check this box for displaying the output graphically. Now, conceptualization is how we define the relationship among our spatial features. We have several choices here, including a user-defined spatial weights matrix. The recommended conceptualization for the hotspot analysis tool is the fixed distance band, so that's what I'm going to use. For our distance method, I'm going to use Euclidean, which uses a straight line distance in the calculation. The last parameter that I'm going to fill out is the distance band. That is the distance that defines the range of spatial interaction among my features. We again want to know the distance where spatial autocorrelation is maximized. So to do this, we're going to run the tool multiple times. We'll start using a distance of a quarter mile, 1,320 feet. Then we're going to increase the distance until we find a peak in spatial clustering. I'm going to click OK to run the tool, and it's just going to take a few seconds. Now, while that's running, I want to let you know that for right now, the best way to examine how spatial clustering changes as the scale of analysis changes is in fact to run the spatial autocorrelation tool multiple times. In the release of ArcGIS 9.2, there will be a new tool called the Multi-Distance Spatial Cluster Analysis tool based on Ripley's K function that will provide a more straightforward way of finding this value. So it looks like we're just about done processing. It's calculating our results for us, and it's going to open for us the graphic that we saw earlier in the slides, the one that shows us about our clustering and our dispersion of our features. Okay, so here we have our results. Let's take a look. We definitely have clustering, and our z-score is 15.4 standard deviations. That'll be important in just a few minutes. And it's significant at the 0.01 level. This is good. I'm going to close the graphic. So now we know that our climbs are clustered, and we know a distance where clustering is significant. But we don't yet know what distance clustering reaches a maximum or peaks. I'll show you that in just a minute. Right now I want to start the Hotspot Analysis tool so it can run while we talk about that distance measure. To locate our hotspots, we're going to use the Hotspot Analysis with Rendering tool, located in the Mapping Clusters toolset. Not only are my stats going to be computed for me, but each feature is going to be symbolized as well. So my input feature class is again going to be my census blocks. And my input field is going to be the ratio column where I've calculated the ratio of vandalism to total crime. Now because this tool is going to do a symbolization for me, it wants to create a layer file. I have a layer files directory where I'm actually going to save my layer file, and I'm going to call it ratio hotspot 3960.lyr. The 3960 is the distance I'm going to use, and I just personally like to put that as part of the name. Now my output feature class is going to be a new data set with my z-scores computed for every feature. I'm going to put that in my results geodatabase. I'm going to call it the same name, but I'm going to get rid of that .lyr. There we go. Took a little while to get into that. Now my distance band that I'm going to use is going to be 3960 feet. That's the distance where crime clustering is the most significant. I'll show you how I know that in just a minute. Okay, so we're done with this dialogue. Let's get it running and talk about that distance band. So how did I know to use 3/4 of a mile? I had actually run the spatial autocorrelation tool multiple times, each time increasing the distance band. Here's the graph of my results. We started with the distance of 1/4 of a mile. We saw that we had clustering of our crimes, and our z-score was 15.4. When I ran the spatial autocorrelation tool for a half mile, my z-score increased to 25.9. At 3/4 of a mile, it was still increasing, this time to 29.6. And at 1 mile, I saw it start to decrease. It's now 29.3. The distance where my z-score is highest is where the spatial processes promoting clustering is most pronounced. That's why I used the 3/4 of a mile, 3,960 feet, in our hotspot analysis. Speaking of which, it looks like our analysis is done. So let's take a look at the results. Remember, we didn't want to place our prevention program where vandalism was simply the highest, but rather where it was a higher than expected proportion to all other crimes. From our hotspot analysis, we can see that vandalism is a larger proportion of crime in the suburban areas of our community. If we looked at the raw counts of vandalism, we might conclude that vandalism is an urban or downtown issue. But that's not what we see when we use the proportion. The areas shown in red are the areas where the ratio of our vandalism to all crime is highest. The blue areas are our cold spots, and that's where the ratio is lowest. We now have recommendations for our community's vandalism prevention program. In this section, we covered how to analyze patterns in spatial data. We discussed tools that assess the overall pattern, and we talked about tools that help identify locations of spatial clusters. I'm going to turn it over to Lauren one last time to answer a few more of your questions.
Thanks, Sandy. We got a question from Yuri in Delta, and the question is, can I add directionality when calculating the global Moran's-I statistic, the spatial autocorrelation tool? And the answer is yes. For all of the spatial autocorrelation type tools, there's a parameter that's called your conceptualization of spatial relationships, and some of the options that you're given are inverse distance, which means that you see relationships as things that are close by are more important than things that are farther away, so kind of a distance decay. Another option is fixed distance span, and that models spatial relationships in terms of a sphere of influence. But the last option is to get your relationship values from a spatial weights matrix file. So you could actually model time, you could model any kind of directionality that you wanted. What you do is you create a file that contains the weight for from and to every single feature, or the features that have a weight, and you would use that weights file when you ran these statistics. We also have a question from Ivy from Atlanta, and she asks, she says, to use these measures you have to aggregate them into polygons, right? You can't just check spatial order correlation or use these tools with just the point locations. And the answer to that question is that all of the tools work fine with points, lines, or polygons. But what I think she's getting at is a lot of times we want to use these tools, hotspot analysis, for data that's incident type data, like crimes or disease. That often comes in as one record per incident, and there's no weight. And in that case, we can still run these tools, but these tools do need a weight. And one way to get a weight is certainly, as she says, to aggregate your crime counts, for example, into census block, or to create quadrats, square polygons, and count the number of crimes in your quadrat and use it that way. But if you have very dense data and you end up where at least a couple of your points are coincident, they have the same x and y coordinates, then you can actually use a tool in the utilities toolbox for the spatial statistics tools called collect events. What collect events does is it looks at all your point data, say it's incident data, and it identifies any points that are coincident, have exactly the same x and y coordinates, and creates a new output. The output is a point feature class with a weight. The weight is the number of incidents that occurred at that location. A lot of people ask us if we have a fuzzy collect events, a tool that'll say, well, these 2 points are really close. They're not exactly the same x and y coordinates, but they're really close. How do I add a fuzzy tolerance to the collect events tool? And there's a good solution to this, actually. If you run the integrate tool, also in the geoprocessing toolbox, it's called the integrate tool. Before you run the collect events tool, what you will be able to do is enter a fuzzy tolerance and snap points that are very close together to the same x and y coordinates, and then get your weighted point data from the collect events tool. Ram from Cedar Falls is asking, what is a z-score? Well, a z-score is simply a measure of standard deviation. So, for example, if the statistic that you're running, spatial order correlation or the hotspot analysis, if it returns a z-score of 2.5, for example, you would interpret that as 2.5 standard deviations. And a z-score is a reference value that's associated with a standard normal distribution. So a very, very high or a very, very low z-score would be found in the tails of the normal distribution. So for these pattern analysis tools, when you get a very high or a very low z-score, what you're finding is that you have a pattern that deviates significantly from a hypothetical random pattern. So to give an example, the critical values for z-scores when you're using a 95% confidence interval are minus 1.96 and plus 1.96 standard deviation. So if your z-score is between minus 1.96 and plus 1.96, you cannot reject your null hypothesis. You're seeing a pattern that could very likely just be one version of a random pattern. But when your z-score falls outside of that range, if you get a very, very high or very, very low z-score like minus 2.5 or plus 5.4, you have a pattern that's probably too unusual to just be another version of random chance. And so we can reject the null hypothesis, and then we want to try to figure out what might be causing, what spatial processes might be causing that pattern, either a clustered or dispersed pattern. I'm going to turn it back over to Sandy.
Thank you, Lauren. Now, before we say goodbye, I'd like to point out some resources available to you. We have a couple of instructor-led classes that will help. We have the Advanced Analysis with ArcGIS class that has a whole chapter on the spatial statistics tools, and we have the Introduction to Geoprocessing scripts with Python that will help if you need to actually get into the Python scripting of the tools. Another resource that we have is the ESRI Guide to GIS Analysis Volume 2 by Andy Mitchell from ESRI Press. You can learn more about this book by clicking the link in the bottom of your seminar window. This is a great resource for learning about these tools. Every chapter goes through the different tool sets in the spatial statistics toolbox. In a few weeks, the recordings of this seminar will be available for free on the ESRI Virtual Campus. The resources listed on this slide and more will be accessible from the recorded seminar. We hope you enjoyed today's seminar, and on behalf of ESRI, I'd like to thank you all for attending.